Alright, so hey guys, my name is Collin Murray, and I'm going to be going over the Comparon experiment that me and my group will be performing in our last lab time. So what is the Comparon equation? This equation was formulated by two French mathematicians, Emile Comparon and Rudolf Clausius, in the early 19th century. And Emile Comparon is also famous for being one of the first people to come up with the second law of thermodynamics and the ideal gas law equation. And what this equation describes is the relationship between saturation pressure and temperature. And it can be also used to find the dependence of pressure on equilibrium temperature when two phases coexist. And the equation is seen right here, and it is the derivative of the saturation pressure over temperature, and this is equal to a ratio of the latent heat of vaporization over the specific volume. And you can also apply the ideal gas equation seen here, with R being the ideal gas constant. So the purpose of this experiment is to use the Comparon equation to solve for the latent heat of vaporization by taking different measurements for a range of temperatures and pressures. And what the latent heat of vaporization is, it's the amount of energy needed to transform a certain quantity of liquid into a gas. And we will also be verifying our experimental results that we calculated by comparing them to the theoretical numbers in the steam tables. Here pictured is our experimental schematic, and this comes with several components, being our 1,000 milliliter flask on top of our hot plate heater seen here with our type K thermocouple. We'll also have our omega analog pressure transducer and mechanical pressure gauge seen here, and our two valves, the air bleed valve and the vacuum control valve seen here with our centrifugal pump and our water reservoir. And we'll also have our computer system equipped with omega data acquisition capabilities. For our data acquisition system setup, first we'll verify that the thermocouple and pressure transducers are connected to our data acquisition system. Then we'll open the PDAC program for our specific experiment. Then we'll verify that the thermocouple and pressure transducers outputs are configured correctly. We'll also ensure that the sampling rate of the experiment is set appropriately at taking samples at every 2.5 seconds. And we'll also verify that the data acquisition system records data for both our temperatures and pressures accordingly. For our experimental setup, like I said, we'll place our 1,000 milliliter glass on our hot plate filled with approximately 2 inches of water. We'll make sure that the water reservoir for the hydraulic vacuum pump contains enough water to cover both the inlet and outlet of the centrifugal pump pipe openings. And then we'll open the vacuum control valve to verify that air is being drawn in, and then we'll run a lengthy leak test on the system. For our procedural steps, we'll turn on the vacuum pump, bringing the flask to the lowest vacuum possible. Then we'll plug in the hot plate, turning it to the highest setting. Next, we'll check that the thermocouple is submerged completely in water, and then we'll start logging the data once the water starts to boil. And during this time, we'll slowly close off the line to the vacuum pump to cause the pressure to rise. And we'll periodically check that our data values make sense by checking with the theoretical values in the steam tables. And we'll open the air bleed valve to avoid any positive pressure buildups. And then after the water reaches a rolling boil at atmospheric pressure, we'll turn off the experiment, and we'll turn off the hot plate and follow all shutdown protocols. So here we have a pressure versus temperature plot for theoretical values, and this was done by, I took 10 values from our steam tables and plotted them. And here you can see that as pressure increases, temperature increases as well, and this is done through a somewhat exponential rate. So for our predicted results, I used 3 of these measurements, and I also reconfigured the Comparon equation to solve for the latent heat of vaporization. And you can see that the experimental and the calculated results are pretty much nearly identical, with the percent error being below 2% for all these data values. And this pretty much confirms the accuracy of the Comparon equation. So some real-world applications, material science uses this to compare phase changes for different materials. Geologists also use this to study rock transformations and mineral transformations as well. It's also widely used in the field of cryogenics as they're dealing with materials that are undergoing extreme cooling and meteorology